and in this video, I'm going to talk about rotary position embeddings that have become so popular for deep learning models these days, right? So let's talk about rotary position embeddings. But before that, let's basically in general talk about how position embeddings are used in these standard transformer-based models. Okay, so let's get started with some notation and some preliminaries. So assume that you have a sequence with W words. So WI words, W1 to WN. So that's basically the original text sequence, right? And you have embedded them from a content perspective using embeddings. So this is basically content embeddings for all of those tokens. WI are tokens and XI are the actual embeddings, token embeddings. Okay. Now, typically what is done is to essentially compute a QKV. So essentially you have for every position, for every token, you essentially take the position and the token at that position and essentially compute QKV. Once you have the QKV, you compute the attention weights, which is basically Q transpose K with a normalization, and then you apply softmax on that. So this is basically exponent divided by the denominator, which is also exponent, the softmax activation function, right? So you get those attention weights, and then essentially you sum over all the n tokens and then do a weighted summation, basically weighted summation over all the values. Right? That basically gives you the revised representation or the transform representation, using self-attention in a standard transform model. Okay. And this for token M. So clearly for token M, you essentially use the query for position M and then key and value for position N. And essentially the way the FQ, FK, and FV, these functions are effectively just additions, right? So essentially you take XM, which is a token embedding, and then you add the position embedding. And typically the position embedding in the standard transform model, the standard proposed position embedding is given by this formula. So they basically use sinusoidal functions so as to compute the position embeddings. So here, if you look at it, I is actually the index, the position, and 2t plus 1. So t essentially here is the index within that position. So for example, if you have to come up with a 512 size representation for position number 1, then your I would be equal to 1 and t would be varying from varying from 0 to 511, because you have to get this 512 sized vector after all, right? So that's that. So essentially absolute position embeddings encode the absolute position of the token using arithmetic addition. So all people do is xm plus whatever is the it's a xi plus pi, where basically xi is the token embedding, pi is the position embedding. And pi is actually computed using this sinusoidal formula that you see here. Okay. So you use the sinusoidal function because they provide good continuity between close positions. So if you have position 0 versus 1, there is good continuity between these positions. And also this allows for the model to scale to virtually unlimited input sequence length, because you can always compute this value no matter whatever, no matter how many different tokens you have, max sequence length that you have. Okay, so that's the absolute position embeddings, and this was proposed in the standard transform model. So Vaswani transform model, this is the absolute position embeddings that were proposed. Now, over time, people came up with this relative position embedding concept. So the relative position, the concept is as follows. So some people essentially initially proposed that you will compute WQ as the position weighted representation for query as WQ times XM, ignore the position embeddings completely. So if you're just using XM, which is the content. Okay, so ignore the position embeddings completely. Okay. For FK and FV, in the sense when you're computing the embedding for a key or a value, you of course use the WK and WV matrices, but then along with the content representation, token representation, you're actually also going to have these position representations. Okay. However, they basically say that these position representations are trainable relative position embeddings. Okay, so as you notice, they are not they're trainable one, and they're relative. Okay, so now what does relative mean? Relative basically means that as you notice here, although you're computing this for the nth token, you're using something called as R here, right? Now what is R? So R is the relative thing. It's a relative distance, in fact, between m and n. In simple words, r is equal to m minus n. That's the simplest form of thinking about it, right? So it's a relative distance between m and n, where m is the position for the query, right? M is the position for the query, and n is the position for the key or the value. N is the position for the key or the value. Okay. However, what they believe is that this relative position information is not useful beyond a certain distance, and therefore they say that, hey, if the relative position is less than a particular value, I'll clip it to r min. If it is greater than a particular value, I'll clip it to r max on the upper side. Okay. So therefore, r is given by this formula, clip of m minus n, where the minimum is clipped to r min and maximum on the maximum side you clip it to r max. Okay. So that was one formulation of relative, the simplest and the earliest formulation of relative position embeddings. So remember, in this particular case, they ignored to include the position information in the query embeddings themselves, but they included the relative position information in the key and the value embeddings. Okay. Now, Transformer Excel paper actually proposed a very interesting and systematic way of dealing with position. They basically said that, hey, all you want to do is to do Q transpose K. You see here we are actually doing Q transpose K, right? And while doing Q transpose K, the initial transformer basically said that, well, we will actually add the content and position embeddings and then do Q transpose K on top of it. So they said, how about actually, splitting this? So essentially, Q transpose K essentially is this, right? So you essentially take XM plus PM, which is basically for, and then you have your WQ, so as to give you Q, and then you take a transpose. And then K basically is WK because, after all, you're using the K, you're computing the key, and this is XN plus PN, right? So now they basically said that you have these terms. How about opening them up, right? Splitting them up, decomposing them, right? And therefore you get 4 terms. The 4 terms really look like that, right? So if you basically decompose just like A plus B into C plus D, and you decompose, you basically get the 4 terms. Okay. So as you look, this is the, as you can see, this is the content term only. This is content plus position, right? Content of nth position and the position embedding for the nth position. This is also content plus position, as you see, content of the nth position, but the position representation of the nth position. And this is position only. This is position only. Okay. Now they basically say, yeah, decompose into 4 parts. That's okay, so that your content and position information is decomposed nicely. However, they basically mentioned that we'll do a few replacements. Okay. And the way they basically did these replacements is mentioned here, right? So they said that let's take the absolute position embedding Pn, which appears here and which appears here, and replace it with relative embedding. They said, yeah, absolute embeddings are not great. So let's basically replace every absolute embedding. Okay. So you will not see any Pn and Pm any longer. So what they said is replace Pn by this relative embedding and, here also. Okay. So that's one change. Another thing they said that, hey, now you're still left with this guy PM, right? So PM, so this guy now and this guy, right? What do you do about that? Well, replace it with 2 trainable vectors, which are not dependent on query position at all. So you basically replace them by U and V, which are independent, of the position. They are basically trainable vectors, but independent of the position. Okay. And lastly, they basically said that, hey, let's not keep this WK the same in both the cases. Let's not keep this WK the same. Let's basically have WK, 2 different WKs. So you can have a, WK which incorporates information about position, but this WK which is basically about content is a different matrix. So basically, also the weight matrix for the key is you use 2 different weight matrices, one for using key towards the content perspective, and the other for using the key for the position perspective. Okay, so this is the history of how position embeddings have evolved over time. Okay, now after that, of course, T5 came in and T5 said, hey, man, just simplify all of this. Let's get rid of all of these 3 terms and essentially just keep this content based term, which is what you see here. And then to incorporate position, well, let's keep a bias term. Okay, and they said that, hey, the bias term is essentially, it's a trainable bias term. And you essentially have for every position pair. So essentially for every position pair MN, you'll just have one trainable bias term, one single number. That's it. Yeah, that's that. Yet another papers basically tried to come up with other kind of formulations. So they basically said, yeah, the content term is good. So in this particular case, they kept the first and the 4th term. So the content term is good and the last term is good. The remaining interactions between position and content can be replaced by a bias term. This is what they used. Later, Deberta came in, and Deberta model basically said that, hey, we will have, again, out of these 4 terms, which are in the decomposition, we will actually keep the first term, which is basically the content term. So, this term is copied as it is here, right? We'll also keep these relative. In fact, it's better to think of it from this side. So, they basically kept the content term as it is. They also kept these relative position terms or relative position embedding terms, this one and this one, right? But then they decided to sort of not have this U and V kind of stuff. They basically just decided to have XN. Okay. So the absolute position embeddings PM and PN are replaced by the relative position embeddings, but they essentially otherwise yeah. They basically took these 3 terms, the first 3 terms, but then they basically just replaced the absolute position embeddings by relative position embeddings. Okay. So that is how things have evolved. So far, I've not talked about rope, by the way, right? So the next step is, of course, to talk about rotary position embeddings. So far, I've talked about how history has evolved from absolute position embeddings to relative position embeddings. And people used to think that relative position embeddings are great. Okay. However, in this paper, rotary position embeddings, these guys actually introduced a special kind of encoding technique where they nicely combine the absolute position embedding and the relative position embedding concepts together. Okay, so we'll see how they do this. Okay, so rotary position embeddings actually encode the absolute position with a rotation matrix. Okay. And again, this is quite mathematical. I'll try to simplify it as much as I can. But some of these are sort of a little difficult to understand from mathematical perspective. But the biggest takeaway is that rotary position embeddings actually incorporate the knowledge of both absolute position and relative position in a very principled and interesting manner. Okay. So you encode the absolute position with the rotation matrix, and you also incorporate the explicit relative position dependency in the self-attention formulation itself. How do you do that? We will just talk about that. Okay. So, well, the entire game is about QM transpose KN, right? Where the query is at position M and the key is at position N for narrow, right? So that's that. And the idea is to basically have this dot product be computed such that it only depends on the content at M, content at N, and the relative position M minus N. So it should not depend on the absolute position that much. The absolute position should not matter much. It should depend solely on the content of M, content at position N, and the relative position between the values M and N. Okay. So in some ways, we are in search of a function G, or rather, we are in search of this dot product kind of function. So essentially, we'll take the query at position M, we'll take the key at position N, and somehow do this dot product such that it's just a function of xm, xn, and the relative distance M minus N. Okay. Now the question, of course, is what is a good choice for FQ and FK, right? So what is a good choice for FQ and FK? The standard transform model basically said a good choice is, you essentially just do WQ. For FK, a good choice is FWQ into, XM plus PM, right? So that's what the standard transform paper said, right? And similarly, they defined FK. But what does rope do? Okay. So we'll talk about what does rope do in 2 parts. One, which is there on this slide, and the second part, which will be there on the next slide. Okay. So the first part basically is about talking when the dimensionality is 2. So this is a special case when dimensionality is just 2. What does dimensionality being 2 mean? The embedding size is just 2. There are only 2 elements in the embedding. Okay. So essentially, XM, if there's a token XM, you have basically XM1 and XM2. That's all that is there in the embedding for the mth token if you have dimensionality equal to 2. Okay. So in this paper, I'm not going to go into those mathematical details now, but in this paper, they say that if dimensionality equal to 2, something that actually really satisfies this constraint, that the dot product should really just be a function of the content at position M and content at position N, and the relative distance M minus N is this. Okay. So essentially, this is how FK should be defined. This is how FQ should be defined. Okay. In fact, the way they should be defined is as follows. You should still have WQ and WK, and you should have XM and XM and XN. Okay, let me write down what basically our transformer paper said. Our transformer paper basically said that FQ should be equal to this, right? And it also said that Fk should be equal to this. Fk should be equal to this xn plus Pn, right? So you see these were additive. So basically the content and the position things were added together. But here, what these guys are saying is that let's make it multiplicative. Let's basically incorporate the absolute position information with a rotation matrix. This is the absolute position information, right? It's incorporated using a rotation matrix. Okay, now it's a little complicated to understand why e raised to I m theta is a rotation matrix. Okay, and I'll talk about that in this part of the slide. But then remember, try to recall essentially e raised to I m theta is an imaginary number, right? So it's basically a complex number. So with the imaginary component and a real component. Okay, so and you can think of it as a matrix, a rotation matrix, and matrices in general are rotation elements. They rotate vectors so as to basically have a rotated output. Okay, so we'll also see a visualization to understand this rotation business slightly in the later part of the video. Okay, so what do they say? They basically say that you can actually incorporate the absolute position with a rotation matrix, okay, like that. And they do it in a multiplicative way rather than an additive way as is done in standard transformer. In rope, it's basically done in a multiplicative way. So you have the token content representation and you have the position representation, which is multiplied in that senses, okay? And then you do that same thing for the key as well, okay? Now, if you want to basically, compute just the dot product, this is how the dot product would look like. You basically are multiplying WQ, WK, you have XM, XN, which is coming up here. But then, the multiplication is not directly very obvious. When you multiply, when you take the dot product, you have to basically take a complex conjugate of this matrix, WK times XN. Okay, a complex conjugate basically is a transpose with the imaginary sign, is imaginary sign plus becomes minus, minus becomes plus in that senses. Okay, so that's the complex conjugate operator as you see here, Okay, now. And then you basically have your EIM theta things, basically which get combined like that. Okay, so that's that. Now RE here stands for the real part of the complex number. So essentially, after all, when you compute the similarity, you only care about the real part of it. So you just take the real part of that thing. Okay, so that's how they have defined for d equal to 2. Now, again, the proof why this is basically a good thing to do is there in the paper if you're really mathematically inclined. Okay. Now, when you talk about theta, what is this theta? So theta is a fixed constant. Okay, they fix theta to a constant value, which is empirically defined in some ways, and we'll look at that in the next slide. How do they fix theta? Okay. Now let's see, this in a little bit more elaborate manner. Okay, so essentially, as you notice here, FQ is WQ XM e raised to IM theta. Okay, now if I look at XM, right, in 2 dimensions, XM looks like that or like that, as I've shown here. Okay. So, and if you look at WQ, in 2 dimensions, this is how it will look like. Okay, just 4 elements in that sense. Okay. And then this EIM theta, it can be actually written as this matrix. In the matrix form, this is how it becomes. Okay. And now to jog your memory, Euler's or Euler's formula, basically said that EIM theta is essentially cos m theta plus I sin m theta. Okay. That's basically some math that you learned way back. Okay. And using that math, it's if you recall, you can actually write this part then in a matrix form like that. Okay. Cos m theta, sin m theta, and then minus sin m theta and cos m theta. Okay. Where the idea is that EIM theta is the real part of cos m theta and the imaginary part is sin m theta, right? So that's that. Now this matrix, this is a matrix. Of course, this is a matrix, really, right? And this matrix essentially captures the rotation by m theta, right? So what is it doing? It's basically taking a vector. After all, when you multiply this w and x, this w times x is just a vector, right? When you multiply the two, you essentially you get a vector, and then when you multiply with this pre-multiply by this matrix, it sort of rotates that vector. Okay, it rotates that vector. And that basically is therefore called as a rotation matrix. How much does it rotate? It rotates by m theta. M theta. Now what is m? Remember, m is the position number for Q. M is the position number for your query. Okay. So that is why, in fact, this is called as rotary position embedding. Why is it called rotary position embedding? Because you take the embedding for the mth position. You take the embedding xm for the mth position. you multiply it with WQ or WK, whatever you want to take, right? If you have WQ, you take WQ. If you want to take WK, you take WK. For mth position, it's WQ, and for nth position, it's WK, right? WK. You multiply, you take the affine transformed word embedding. This is called affine transformed word embedding, right? And then you multiply by EIM theta and you multiply by EIN theta. So you rotate it, you know? So this multiplication, remember, is rotation. So you rotate the affine transformed word embedding by an amount decided by the angle multiples of the position index. This angle multiple of the position index, right? And that is why it's called as rotary position embedding. Remember, it's multiplicative in nature, unlike the standard transformer, which has position embeddings, which are additive in nature. Now, what we looked at was basically a way of computing the rotary position embeddings using this matrix in 2 dimensions, right? Now, what happens if you generalize it to higher dimensions, like say D dimensions, where D can be anything now, 512, 768, or 1024. You know, these are popular dimensions which are used by transform models these days. So they show that, you know, you can actually do that by just encoding your query or key using this matrix. Of course, you have to multiply W into X, but then you have the rotatory matrix, the rotation matrix, essentially given by this in D dimensions. Okay. So essentially, it's given as follows. You you divide the D dimension space into D by 2 subspaces, and you see you have these D by 2 subspaces. So essentially, you know, 2 by 2 and D by 2 of them. Sorry, D by 2 of them. So you divide them into these subspaces, and you have a block diagonal rotatory matrix. Okay. Now the theta guys here, you know, you see many thetas here. Those thetas are actually fixed in the same way as was done in the transformer paper. Okay, so the theta there also was fixed as this guy. You know, if you recall, I'll just go back and show it to you in the transformer paper. You see your sine k theta. So sine k theta is basically, so what is the value of theta? Theta is 10,000 raised to minus 2 divided by d. You have the same guy appearing here. 10,000 raised to minus 2 I divided by d, because, you know, it's basically combining the odd and even part together. Okay, so that's that. Okay, so that's good. So now remember this thing basically just tells you the position encoded representation, or the rope encoded representation for a query or a key. But what you're interested in, self-attention, is to multiply the two, right? So remember QM transpose into you know, KN into KN, right? So QM transpose into QN, basically, you know, if you use this formula here, it basically becomes that. And then you can basically take out the terms X transpose and XM there. Well, this should be XM transpose. Sorry for that. XM transpose and XM there, and your WQ and you know, WK terms there, and then you combine these RD terms together so as to get RD n minus M. Okay. So you know, this n minus M guy is basically now a relative representation, as you see, right? So far they were all you know, if you basically just use this thing, it was essentially absolute representation. But now when you do the dot product, interestingly, when you do the dot product, essentially all you need to do is to care about the relative differences. So essentially, if you know, if you're rotating the matrix by m times, and then you're rotating the matrix by n times, you know, m times and n times for the query and the key, when you do the dot product, you basically rotate the matrix by m minus n theta times, right? That's that. It's as simple as that. And that is why, in fact, I mentioned that although you encode the absolute position with the rotation matrix, you know, you incorporate explicit relative position dependency in the self-attention formulation, right? This is for 2D, and on the next slide, I basically showed you for general D dimensions, Okay. So, you know, now sort of summary out of all of this is that in contrast to earlier position embedding methods, rope is multiplicative in nature. So whether it was, you know, relative position embeddings, or it was absolute position embeddings, you know, they were both additive in nature. You take content thing and you take position thing and you just add that up. But this one is multiplicative in nature, and it naturally incorporates relative position embedding through the rotation matrix product instead of altering terms in the additive position encoding way, right? So it basically has your absolute position encodings, you know, done in the rotatory matrix, while the relative position embeddings are done through the dot product. Okay, it sort of exploits the dot product part of the self-attention mechanism. Okay. So rho represents token embeddings as complex numbers. It represents their positions as pure rotations. So positions are represented as pure rotations, ei raised to m theta, ei raised to n theta, and so on. Right? And then, the nice idea is, this is a very, very key intuitive point. It does not really require math to understand this. So, you have a query, you have a key, right? And they're at some positions, m and n. Now, the idea is that if you shift both query and key by the same amount, you shift by the same amount, m minus n does not change. And since m minus n does not change, essentially the angle between them does not change, and therefore the dot product remains unchanged. That's the nice part. Okay. So this basically satisfies the exact condition that we wanted to have. That overall, the multiplication, the dot product in the self-attention Q M transpose Kn will only depend on the distance between the two, distance between the query and the key, and not really on the absolute value, right? Or other, it won't change if you basically move the query and the key by the same measure. Okay, if you shift both of them by the same amount. Okay, so here is a simple representation of the implementation aspect, and this is shown for d equal to 2. Okay, so if you basically have multiple words, and you, of course, these are their positions 1, 2, 3, 4, 5, 6. Okay, you decide the theta for these positions using this formula, and then you have your x vector. You multiply that x vector by w. You multiply that by w. And then, essentially you rotate it by m theta. So after you have multiplied it by w, you want to rotate by m theta. And what happens is that this x1, x2, after you have obtained, after multiplication with w, this x1 and x2, essentially the vector here, it gets rotated and moves there. And that basically is your position encoded representation. You use that for query, you use that for key as well. And that gives you position encoded representations for queries and keys at each position. Okay, good. So, this rotatory position embeddings actually have a nice property of long-term decay. So the property basically says if the query and the key, the relative distance is larger, then the inner product, the self-attention inner product reduces. Okay, so the inner product sort of decays when the relative position increases. If the query is very far away from the key, then the self-attention value should be small. So that satisfies intuitive understanding as well. A query should sort of really get its revised representation based on keys which are close by. Right? So that's basically a nice thing, which is automatically incorporated, as you see in this plot as well. As the relative distance between the query and the key increases, your QM transpose KN sort of reduces as well. Okay. Now you might be thinking, hey, how computationally inefficient this multiplication and all of this is? Well, it's not inefficient. And since this matrix is super sparse, what you could do is to really take this R and this X, and actually you can actually just write it in very, very simple terms like that. You can ignore all the zero terms, and if you just pay a little attention, you can take all the cost terms together, and you can just do element-wise multiplication with the X vector. And you can take all the sign terms together and then do element-wise multiplication with the appropriate signed X vector. And that essentially is the same as this guy. But this is super efficient to compute. This is actually very, very efficient to compute rather than doing a full matrix multiplication, a dense sparse matrix. I mean, it's a sparse matrix. So why do the full multiplication? Rather just do sparse matrix multiplication. And that gives you a very efficient implementation. Yeah, well, people observed in their original paper that yes, rope embeddings could give them better results compared to standard transformer on machine translation, English to German machine translation task, right? The rope embedding based transformer, they called it Roformer. Okay, so this improves on the blue score for the machine translation. They also observed that if you basically compare this Roformer with the BERT model, they observed that across several glue tasks, you actually tend to get better results. Okay. What they also observed, this is of course fine tuning, right? This is of course fine tuning of the transform model on various benchmark data sets. But if you're doing just language model pre-training also, so you observe that if you compare pre-training on the MLM loss between Roformer and BERT, you actually observe that the Roformer, which basically uses rotatory position embeddings, actually converges faster, right? So the MLM loss reduces faster as you increase the number of steps. Also, if you compare performer model with rope and without rope embeddings, you observe that the performer model without with the rope embeddings essentially again converges faster, right? The blue line converges faster compared to the orange line. Okay, so that's the video. Let me summarize. So rope is rotary position embeddings. It sort of represents token embeddings as complex numbers and represents their positions as their absolute positions as pure rotations. And it exploits the dot product property of self-attention so as to encode the relative position encoding relative position information between the query and the key. Okay, it has been shown to be better than existing absolute and relative position embedding methods across several models and several tasks. Not just the ones that I showed to you, but also after that, several people basically have used rotary position embeddings. In some ways, it has become standard in today's world. Okay, so hope you enjoyed the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.